Hi, in this video I'm going to demo a containerized Ceph deployment on a Kubernetes cluster running on Google Compute Engine. So let's go ahead and get started. First off, you'll want to have the Google Cloud Platform SDK in order to have the gcloud command, among other things. And we'll go ahead and set some defaults in order to work with the command line. I'm going to set the region to the region that's closest to this client, and we'll do the same for the zone. And we'll set the project to the project that's already been created on the web interface. I've already created this project in the Google Cloud console. So we'll go ahead and clone the repo that contains the scripts in order to automate the deployment of the Kubernetes cluster on Google Compute Engine. So here you'll see several scripts. Particularly the cube up one is the one we'll be using, which will require setting 3 variables, num controllers, num workers, and the Kubernetes version that you would like to use. And this particular script will invoke several of these other scripts in here in order to automate the deployment. So let's go ahead and set controllers equal to 3 just for HA demonstration purposes, and num workers 10. And let's go ahead and use Kubernetes version 1.5.1. Now we're just about ready to launch here, but this will give us 13 nodes when it's complete, and that will include those 3 controller nodes and 10 worker nodes. 10 of those worker nodes will consist of 3 CephMon nodes and 7 storage nodes to run the Ceph storage cluster. The storage cluster will include things like OSDs, MDSs, RGWs, and any CephFS or RBD clients. So let's go ahead and launch this. And we're going to go ahead and redirect everything to a log so that we can tail that log. And I'll return back when this is complete. All right, the script has completed, and you can see it took just about 27 minutes to complete. So once the script is done, you should have a working Kubernetes cluster with remote access to it using kube control. So let's just take a look at our instances list here. And you can see that we have 3 controllers and 10 worker nodes. And they should all register. And we show here that we have 10 worker nodes that are ready. For this next part, we're going to need access to some of the resource YAML templates inside of the Ceph Docker repo. So let's go ahead and clone that. Here we have some scripts that will go ahead and automate the creation of the Ceph cluster. But before we go ahead and continue with that, we need to override some of the default settings. For example, we have a OSD cluster network and OSD public network that we need to overwrite. The default is something like 10.244.0.0/16, but we need to instead use the cluster seeder that we specified when we launch the Kube Controller Manager, and you can reference some of the automated scripts that did that to see what that uh, cluster seeder looks like. So let's go ahead and export the variables that we'll need. So the cluster network that we'll be using is this one right here, which was passed to the Kube Controller Manager. And we'll go ahead and export a couple of variables here that will define the cluster network and the public network to use. And we can see that we've defined those variables. In the next part, we'll override the default number of placement groups. By default, 128 is used for the OSD pool default placement group number, and the default number of placement groups for placement. So in order to maintain a health OK status for our Ceph cluster, we're going to decrease the number of placement groups. This is so that we can maintain the same number of OSDs to stay within our CPU quota limit without having to increase our CPU quota. Now we'll set our current context to use the default context with the Ceph namespace. Default context, and we'll specify Ceph namespace. So now all these subsequent kube control commands will default to the Ceph namespace. So now we're ready to generate the Ceph Kubernetes keys and configuration. So we'll create the secrets, and this will create the Kubernetes Ceph namespace and then create the secrets in that namespace using the generated configuration and keys. And you can see all of the secrets that were just created. So now we're ready to start deploying some of the Ceph components. So let's deploy the cephmon service and the cephmon deployment. And let's go ahead and watch as the containers are creating here. And now you should have the pods up and running with an IP address and the nodes that are running and hosting those pods. So you should now have, we now have the deployment that looks basically something like this. Let's go ahead and create the Ceph OSD daemon sets and create the Ceph MDS component. Now, in order to deploy the Rados gateway component, we need to adjust the Rados gateway service to instead use the node port type, because using the load balancer type won't work since we didn't configure the cloud provider when bootstrapping this cluster. So we need to go ahead and adjust that. And now we're ready to create the Rados gateway service and deployment. So in order to actually launch a lot of these resources, a lot of these pods, we need to actually have nodes that are labeled as storage nodes. So you can see here the MDS is pending and the Rados gateways are also pending, and the OSD daemon sets are not launched until we have a node that's labeled as a storage node type. So let's go ahead and do that, and for this purpose we'll go ahead and just label all of the nodes which are not running cephmons. We'll label those nodes as storage nodes. So you can see here that the cephmons are running on nodes 3, 1, and 5. So we'll go ahead and store the nodes here. Those are the mon nodes that we should have. And we'll go ahead and save off the unused nodes. And so we'll go ahead and label the remaining nodes, unused nodes, as node type storage. Once you've done that, you should see the pods being launched. Once all the pods are up and running, you should have a cluster that looks like this. So we have all these components that are up and running now. And so we can check the health status of the Ceph cluster. We will grab one of the monpod names and store it in this variable. Just call it monpod name here. You can see there that it's set accordingly, and then we'll just launch a command, check the health status of the Ceph cluster, and you can see that it's health okay. And we have 3 pods, 3 Ceph mons that are up in a quorum, and 7 OSDs that are up and in, as well as the MDS that's up and active, and everything looks okay. Now we will test the Rados gateway, and to do that we need to grab the Rados gateway node port that was assigned, and we'll just run this command here to extract that. And you can see that it's set there, and we're going to have to create a firewall rule in order to allow access to the Rados gateway service on that port that we just grabbed. So the firewall rule was created for the Rados gateway service, and now we'll grab the node 0's public IP in this particular command, and we'll save that in the node public IP. And this is just to make it easier to now see if we can access the Rados gateway interface using these variables that we've saved. So you can see there that we can now access the Rados gateway interface. Now we'll go ahead and grab the name of the Rados gateway pod. Using this command here, we want to just save off that so we can start executing commands on it. And now we'll go ahead and execute a Rados gateway admin user create command against that pod. This will create the Rados gateway user that we'll use to access the object storage. And now we'll set up the S3 client test with the IP and keys that were just created here. And we'll go ahead and overwrite the client script with that access key. And now we'll grab the S3 secret key. And then let's go ahead and replace that as well. Now using the node public IP that we saved off previously for worker 0, we'll go ahead and overwrite the IP address in the script. So we'll talk to that host and on the port specified by the Rados gateway node port that we were given. So now that we're ready, we can launch the S3 client test. And in this test, you'll see we'll create a new test bucket, and then we'll have here's the name and the timestamp for that test bucket, and we'll go ahead and add a public and private objects with some dummy test data in each of them and print out the URLs for each of the objects. So here we have the hello.txt object, and if we grab this, we'll see that we output the hello world ASCII that's stored in that object. And then if we do the same for the secret object, you can see that the secret plan's ASCII text is output as well. So now we will do some tests for CephFS and RBD. And in order to do that, we need to actually install the Ceph and RBD utilities on all of the nodes. And the nodes that we have are actually running Ubuntu 1604 Xenial. So we can go ahead and install those utilities programmatically. So we want to do it on all 10 worker nodes. So we're going to go ahead and run an apt-get update on each of those nodes. And then we'll go ahead and install CephFS common and Ceph common. Once the Ceph and RBD utilities are installed on all the nodes, we can go ahead and mount the CephFS in a pod. One of the requirements for doing that is that we need to add the admin client key to the Ceph namespace. This has already been done by the create secret script that generated and created the secrets. So the next step, we need to actually configure the cephmon IPs to use in order to actually contact the Ceph monitors. And unfortunately, we can't, the Kubernetes installs do not configure the nodes resolve.conf file to use the cluster DNS by default. So we can't rely on using the Ceph monitor DNS names in this example. So we'll go ahead and grab the mon pod IP. We'll set that in the variable here. And then we'll overwrite the cephmon DNS with the mon pod IP in the CephFS test here. Go ahead and create the CephFS test, and let's go ahead and watch it. And we can see it's already running. So now let's go ahead and execute the df command inside of the container, and we can see that the CephFS mount is mounted, and it's a type Ceph file system. Let's make sure that we can actually read and write. To this particular mount. And there we go. In this part, we'll test mounting a Ceph Rados block device in a pod. But first, we need to create a Rados block device volume. So using the mon pod name that we've previously saved off, we can go ahead and create a test Rados block device volume. Let's do this with like 20 gigs, for example. Now that that's created, we can go ahead and check, make sure it looks okay. And we can see here that we have a 20 gig RBD image. So the same caveats apply for the Rados block device as CephFS volumes. So we need to edit the pod IP accordingly. So we go ahead and replace the cephmon DNS with the monitor pod IP address in the Ceph RBD test resource that we're about to create. And if we go ahead and create that, we watch it, it's already running. So let's go ahead and take a look at it. And we can see that we have a Rados block device mount with 20 gigs size. And that matches the Rados block device image that we created. So if we want to go ahead and test this, similarly, we can just make sure we can read and write to it. Just output some test data, redirect it to a test file. And let's go ahead and cat that. And there we go. So that shows that we can read and write to both a CephFS and RBD mount points. In this section, we'll talk about persistent volume claims with static provisioning, both with Rados block device and Ceph file system. So for persistent volume claims with static provisioning, we need to add the Ceph admin keyring as a Kubernetes secret so that our persistent volume resource has the necessary permissions to create the persistent volume. The name that we give to that Ceph admin keyring secret needs to match the name given to the secret in the persistent volume resource that we create later. So let's go ahead and create the secret, and we'll use the monpod name that we've previously set in our variable, and we'll go ahead and get the client admin keyring. And let's go ahead and create that secret. And we can see that it's been created. And now we'll create the RBD image for the persistent volume. We're going to make this 10 gigs and refer to the image as Ceph RBD PV test. And the output looks okay. We have a 10 gig RBD image that's ready to test. Similarly as before, we need to create the, we're almost ready to create the persistent volume resource, but we need to modify the cephmon DNS to use the IP address. So again, we have our monpod IP saved off in that variable, so we'll go ahead and modify the persistent volume resource. And we go ahead and create that. If we get the persistent volume, we should see it there. We can also do a describe, get some more details, and we can see here that the IP address of the Ceph monitor that we just set in the resource corresponds to that IP there, and we have a Rados block device type. Here's the RBD image that we just created, and we can see that the status is available. Now we'll go ahead and create the persistent volume claim. And similar, we can see that claim here and get some more details on it as well. And we can see that here's the status is it's bound, it's 10 gigs as well, and here's the volume that it corresponds with the persistent volume that we created. So now we need to create a test pod that's going to use this persistent volume claim. So we have a persistent volume claim RBD pod as well, and we can go ahead and create that. And it's already running. Pod 1, and if we grep for RBD, we should see an RBD mount point corresponding to the 10 gig size that we just created. Similarly, we can go ahead and output some, read and write some dummy data. Excuse me. And we can go ahead and cap that as well. And so we show that we've set up a Rados block device persistent volume claim with static provisioning, and we have this test pod here that was able to consume it. Similarly, we can do the same for Ceph file system using the same mon-pod IP variable and the Ceph admin secret that we've created for the RBD test. We can go ahead and perform a test for CephFS. So here we'll go ahead and overwrite the cephmon DNS with the monitor pod IP address. Go ahead and create the persistent volume. Get some details on it. And we can see that we have a persistent volume with an available status here. Let's go ahead and create the claim. And we can get some details on the claim, see that it's bound to the CephFS persistent volume, and we're ready to go. So let's create a test pod to utilize the persistent volume claim. And we can go ahead and it's already running, so we're ready to go ahead and verify that we have. We have a Ceph file system type, and we have this mount point here. So if we want to also perform a read and write test, we can do so. And there we go. We show we've done a Ceph file system persistent volume claim with static provisioning, and we have this test pod here that was able to consume it. For this last piece, I'll demonstrate persistent volume claim with dynamic provisioning, and we'll be utilizing Rados block device for this demonstration. And the prerequisites for this do require Kubernetes version 1.5 or newer, and we need to have the Ceph and RBD utilities installed on the controller nodes, and any worker nodes that are going to host Ceph monitor pods or any of the test pods as well. So let's go ahead and install the RBD command line utility on the controller nodes. We've already installed it on the worker nodes previously, so now we just need to install it on the controller node. So let's go ahead and update. And install CephFS common and Ceph common. For persistent volume claims with dynamic provisioning, we need to add the Ceph admin keyring as a Kubernetes secret to the same namespace that's defined in our storage class resource. And this is so that it has the necessary permissions to create the dynamically provisioned volume. In this example, we'll just use kubesystem as the namespace. And the name that we give to the Ceph secret admin keyring must match the name that's given to the admin secret in the storage class resource that we're going to create a little bit later. But for now, let's go ahead and create the secret and use the same monpod name we set previously. So here we'll create the secret and name it Ceph secret admin from the literal key that we're passing here with the admin keyring variable. We're going to put that in the kubesystem namespace, and we need to specify the Rados block device type. So now if we do we see here that we have a Ceph secret admin secret with a RBD type. So now we can create the Rados block device storage class. In this particular case, we're going to name it slow, and it's going to use the RBD provisioner. In order for us to use it, we need to specify a comma-separated list of CephMon pod IPs, and that's so that the storage class will be able to access the Ceph monitors. So let's go ahead and grab the monitor IPs. You can see there, those are it. Let's just create a comma-separated list of them. So you can see here, it's just programmatically doing this. And we can go ahead and replace the monitor's Ceph, the Ceph monitor IPs in the storage class resource with the comma-separated list of CephMon IPs that we have in our particular case here. So if we grep for monitors in the storage class, we can see that we've set that accordingly. We can now go ahead and create the resource, create the storage class resource, and do a describe on it. And we can see here that it's named slow, and it uses the RBD provisioner. And here are the parameters that we're specifying. Here's the Ceph secret admin secret name that we just created. It's in the kubesystem namespace and the list of monitors that it needs to contact. And importantly here, we have a pool named cube and a user ID cube with the Ceph secret user secret name that we'll create here next. The Cube Controller Manager is now able to provision storage, but we still need to be able to map the RBD volume to a node. So the mapping should be done with a non-privileged key, and we can use an existing user from our Ceph cluster, or we can just create a new user. In this case, we'll just create a new user and pool to avoid any confusion. And this particular user and pool needs to match the names provided in the storage class resource we just saw here with pool cube and user ID cube. So let's go ahead and create those. We'll go ahead and specify 64 placement groups for that pool, just for demonstration purposes. All right, now that we have that, we can go ahead and export that into a variable here for cube keyring, and we'll use that keyring to specify the keyring for the secret that we'll create here. So here we'll create the Ceph secret user from that cube keyring that we've extracted from the cube user, and it'll be type RBD as well. So now once we have that, we're ready to provision and use the Rados block device storage. So we need to create a persistent volume claim in our Ceph namespace, and that'll use the storage class configuration that we just created. So now that that's created, we can see here that we have a Rados block device dynamic persistent volume claim in the Ceph namespace corresponding to the slow storage class, and we can see that the status is bound. If we do describe on it, we can see a little bit more information. You can see that the Rados block device image is a dynamically provisioned image, and it uses the Rados block device pool cube with the user cube that we just created. Now with our storage dynamically provisioned, we can create a test pod to consume that. And once that's created, let's go ahead and run the df command. And we can see that we have the Rados block device mount, and it corresponds to 3 gigs, which is equivalent to the persistent volume claim capacity that we specified. So similarly with the other examples, we can go ahead and just perform a simple read and write test. And that shows we've set up a Rados block device persistent volume claim with dynamic provisioning, and we have this test pod here that was able to consume it. Thanks for watching.